Now in this class, we will be seeing the detection of AM waves. So the process of detection or demodulation. So we can call it as either detection or demodulation, which is exactly the inverse process of modulation. So this will be done at the receiver side. So the process of detection or demodulation means recovering the message signal from an incoming modulated wave. So for the demodulator, the input will be modulated wave and the output will be message signal. Coming to the modulator, at the transmitter side, so for the modulator we have two inputs. One is message signal or modulating signal, and the second one is carrier signal, and the output will be modulated wave. So coming to the receiver side, for a demodulator or detector, the input will be modulated signal. So it can be AM, FM, or PM signal. So AM signal, that is modulated signal, will be the input, and the output will be the message signal or modulating signal. So as said, detection is the inverse of modulation. So coming to the square law detector, so this diagram shows the square law detector. So a square law detector is obtained by using a square law modulator for the purpose of detection. So since as we have used square law modulator for generating the AM wave, we can use the same device in order to detect the AM wave. So we use a nonlinear device similar to the square law modulator. So this AM wave is passed through a nonlinear device, and then it is passed through a low-pass filter. So in case of square law modulator, we have used band-pass filter, but in case of square law detector, we use low-pass filter. Because in modulator, we need the frequencies which are centered around FC. But coming to the detection process, we need to detect the message signal. Hence, we'll be using low-pass filter F, which is centered around FM, because we need the message frequency. And then we use a DC blocker in order to eliminate any DC components present after this low-pass filter. So as we know, the nonlinear device can be modeled as V2 of t is equal to A1 into V1t plus A2 into V1 square t. So now the input to the detector is obviously the standard AM wave. So V1 of t can be written as AC into 1 plus Ka m of t cos 2 pi fc t. So this is the AM wave which is given as the input to the nonlinear device. So now if we substitute this V1 of t in V2 of t, we get V2 of t is equal to A1 times, this is V1 plus A2 times V1 square. So after expanding these terms, we get the first term will remain as it is and the second term will become. So since this is a square term, so A2 into AC square and this 1 plus Ka m of t whole square will be 1 plus 2 Ka m of t plus Ka square m square t. And coming to the last product, cos square 2 pi fct. As we know that cos square theta can be written as 1 plus cos 2 theta by 2. So this cos square 2 pi fct can be written as 1 plus cos 4 pi fct by 2. So this is the final expression of the nonlinear device. So here from these terms, the desired signal is this part, A2 AC square into Ka m of t. So here this A2 into AC square multiplied with this and multiplied by 1 by 2. So this 2 will be cancelled out. The desired signal will be A2 AC square Ka m of t. And this term is due to the A2 into V1 square t term. So this has been obtained from this part, A2 into V1 square t. Hence, it is named as square law detector, because by using this square law, we are obtaining the message signal. Now, when the signal is passed through a low-pass filter, then this component can be extracted because this is centered around FM. But when we pass this signal through the low-pass filter, so this is not the only contribution within the baseband spectrum, because A2 AC square Ka square m square t by 2 will give rise to the plurality of similar frequency components. So if you observe here, this is the message signal, and we also have this m square t term. So when we plot this in frequency domain, it will be outgoing frequencies from 0 to 2 FM. So since we are passing this through a low pass filter, which is centered around, which is having cutoff frequency FM. So some frequency components, that is from 0 to FM, this signal will be passed. So along with this required signal, this m square t term will also be passed. So in order to reduce this effect, what we can do is we can take the ratio of wanted signal to the distortion. So this is the wanted signal, m of t is the wanted signal, and this m square t is not the required signal. So it is the noise or distortion. So what we can do is by taking the ratio of wanted signal to the distortion, it can be written as a2 ac square ka m of t. So this is the required signal, and this is the noise. It is m square t term. So if we simplify this, we get 2 by ka m of t. So if we make this ratio large, so since it is defined as the ratio of wanted signal to the noise or distortion. So if we make it large, this wanted signal will be large and distortion will be less. So to make this ratio large, what we can do is we can decrease this denominator. So if this value is very less, then the ratio becomes large. So we can choose this magnitude of k m of t small when compared to 1. So when this value is very less when compared to 1, this ratio will be large, and hence the wanted signal will be more when compared to the distortion or noise signal. So this is how we can use square law detector in order to detect the standard AM wave. Simply we are using a nonlinear device and a low pass filter to detect the message signal. And coming to this DC blocker, where it will be used is, so here if you see, we have this DC component, A2 into AC square by 2. So this is the DC component. So it is not having any frequency components. So in order to remove this, we are using this DC blocker. So by using DC blocker and low pass filter, we can detect this message signal. And in order to reduce this noise due to m square t term, we can choose this magnitude k m of t very small when compared to 1. So this is one of the detector to detect the AM waves, and the second one is envelope detector. An envelope detector is a simple yet highly effective device that is widely used for demodulation of a narrowband AM wave. So it is called narrowband because the carrier frequency is large when compared to the message bandwidth. We have already discussed that this carrier frequency is always greater than the message signal bandwidth. So this envelope detector is the most widely used demodulation technique for narrowband AM waves when the percentage modulation is less than 100%. So this envelope detector will work only when the percentage modulation is less than 100%. So if we remember, while discussing the different cases in AM wave, we have seen that for over modulation case, that is when percentage modulation is greater than 100, there will be some phase reversals at the zero crossing, and it will cause envelope distortion. So this envelope detector will work only when the percentage modulation is less than 100%. So it will not work for the over modulation case. So ideally, an envelope detector produces an output signal that follows the envelope of the input signal exactly. So it will exactly follow the envelope of the input signal. So this is the reason why it will not work for the over modulation case. And this envelope detector simply consists of a diode and a resistor capacitor filter. So here at the input side, we have a standard AM wave and a source resistor RS. We have an ideal diode and a capacitor and a load resistor RL. So the output will be taken at this load resistor RL. on the positive half cycle of the input signal, so when this input is positive, then this diode will be forward biased. So once it is forward biased, since it is ideal diode, since we are assuming the diodes are ideal, so this will be short circuited and there will be a path in this loop. So this capacitor will be charged to the peak value of the input signal. So during the positive half cycle, this diode will be short circuited. And initially, since the voltage across this capacitor is 0, so this capacitor will be charged to the peak value of the input signal. And now when the input signal falls below this value, so once this is charged to the peak value, and when the input decreases below this peak value, then again this diode becomes reverse bias, because the voltage at the N side is more when compared to the P side of the diode. So this diode will be reverse biased and it will be open circuited. So the voltage across this capacitor will be discharged through this load resistor RL. Since this is open circuited, this part, so the voltage across this capacitor will be discharged through the load resistor RL. Now this discharging process will continue until this the voltage at the P side is greater than the voltage across this capacitor. So again, when the input signal becomes greater than the voltage across the capacitor, the diode will conduct again and the process is repeated. So when this voltage at the P side is greater than the N side, the capacitor will be charged through this loop, and when the diode is reverse biased, the capacitor will be discharged through this second loop. And we assume, as said, we assume that the diode is ideal and it is having an internal impedance of Rs. So now this charging time constant, that is Rs into C, must be short when compared with the carrier period. So carrier period is given by 1 by Fc, where Fc is the frequency of the carrier. So this charging time constant Rs must be small when compared to the carrier period. That is, Rs into C should be less than 1 by Fc. Why it needs to be small? Because this only then the capacitor will charge rapidly and thereby follows the applied voltage up to the positive peak. So only when this time constant is small when compared to the carrier time period, the capacitor will be charging very fast, so that it will exactly track the input voltage. And on the other side, this discharging time constant, that is RL into C, must be long enough to ensure that the capacitor discharges slowly. So while discharging, this capacitor should be discharged very slowly. So we need to make sure that this RL into C is large when compared to the carrier time period. So RL into C should be greater than 1 by Fc, and it should not be very long, so that the capacitor will not discharge at the maximum rate of modulating wave or message signal. So if this discharging rate is kept very high, then we cannot track the message signal. So it should be less than the 1 by W, where W is the bandwidth of the message signal. So the result is that the capacitor voltage or the detector output is very nearly same as the envelope of AM wave. So when the charging and discharging time constants are designed as shown here, so the output of this envelope detector or the voltage across the capacitor will be same as the envelope of the AM wave. And usually the detector output will have a small ripple at the carrier frequency, which can be removed by using a low pass filter. So if we consider an AM wave, so this yellow line represents the output of the envelope detector. So here at time t equal to 0, when the input is being positive, so here since this voltage is greater than the voltage across the capacitor initially, so the diode will be forward biased. The capacitor will be charged rapidly until the peak value. So once it is charged to the peak value, now input is being reduced. So when the input is less than the capacitor voltage, this diode will be reverse biased, and hence it will be discharged slowly. So since we are making sure that the discharge time constant is large, so the discharge rate will be slow and it will be slowly discharging. Now again here the input voltage is greater than the capacitor voltage and hence it will be charging. So the discharging will be continued like this, and we can track the envelope of the AM wave like this. So since we can observe here that there are some ripples in the envelope of the wave. So once if this waveform is passed through a low pass filter, we can clearly track the message signal, which will look something like this. So without low pass filter, the waveform will be like this. And after passing it through the low pass filter, these ripples will be removed and we get the message signal. As discussed, if the discharge time constant is very small, so here we can observe that the discharge is also happens at the very fast rate. So charging is being done rapidly and discharge is also being done rapidly. So it will be fastly discharged and hence, so we'll get some triangular wave like this. So if the discharge time constant is too small, so we cannot exactly track the message signal. And on the other hand, if we make the discharge time constant very high, so what will happen is, so until this point there is no problem, but if the discharge rate is very slow, so we can see that since it is very slowly being discharged, we cannot track these peaks. So if the discharge rate is very large when compared to the time period of the message signal, so this is the message signal, the envelope. So if it is very large when compared to the variation of this message signal, we cannot exactly track this message signal. So this is the reason why this RC should not be too large and too small. So it should lie between these two values, 1 by Fc and 1 by W. So it should be greater than 1 by Fc, so that here at these points the discharge is slow, and it should be greater than 1, it should be less than 1 by W, so that it will also track these points. So, we see the envelope detector. The circuit is something like this. We have a diode, the capacitor, the load resistor. Here the input is the AM wave. This is RS, C, and this is the load resistor RF. Now if we plot this AM wave, which is the input, so this is the AM wave. So when this AM wave is given as input to this envelope detector, so at time t equal to 0, so just after 0 plus, t equal to 0 plus, the input voltage is positive value. So initially the voltage across this capacitor Vc will be 0, and once we are applying a positive voltage, so this diode will be short circuited, because the voltage here it is positive voltage and here the voltage is 0 initially. So what will happen is, this will be short circuited like this. So now in this part, since it is short circuited, it will be charged through this capacitor, and this charging time constant value is Rs into C. So this as the input is increases from here to here. So let's say this is the peak value Vp at time t equal to Tp. So if you plot the output waveform, so since the diode is short circuited, the capacitor will be charged to the maximum value Vp. So the output will be something like this. So until here the capacitor voltage will be charged. Now after this point, you can see that this input voltage is being reduced from the Vp. So here now the voltage here will not be 0. So the voltage here is Vp, peak value, and here this input voltage is less than Vp. So what will happen is this diode will be open circuited. So when it is open circuited, so this one will be open, and we have this path, closed path. This is and this is RL. So now in this case, this one will be discharged. The maximum voltage Vp will be discharged by this constant time constant RL into C. Charging time constant is less than 1 by Fc. Since this time constant is very less when compared to one carrier time period, so this is being charged very fastly. Only when this time constant is small when compared to the time period of the waveform. So here the waveform that is being followed is carrier. So when the time constant is very small, it will be charged very fastly. And coming to the discharge rate, so it should be greater than 1 by Fc. So when it is greater than 1 by Fc, that is time period of the carrier, it will be discharged very slowly. So since it is being discharged slowly, it will discharge something slowly like this. So if it is being charged very rapidly, then waveform will look something like this. So this is not the actual envelope. So in order to track this envelope, we need to make sure that this discharge is being done very slowly. So it will be discharged until this point. Now again here at this point, the voltage, input voltage is greater than the capacitor voltage. So it will be charged to this peak value. So here again it will be discharged. It will be charged, discharged, something like this. So like this, the envelope will be tracked. So once we get this black waveform is the input wave, and this red one is the output wave. So like this, we can track the envelope of the AM wave. And here, one more condition that we need to satisfy is this should be less than 1 by omega. That is the time period of the message signal. So why it needs to be less than this means? So let's say if it is very high, so what will happen is, if the discharge constant is kept very high, so it will be slowly discharged like this. So if the RC value is very high, so it will be discharging something like this, and we cannot track these peaks. These peaks cannot be tracked. So that is the reason why it should be less than the 1 by omega, that is time period of message signal. So if you see, this is the message signal. So if it is less than this time period, then we can easily track these lower portions also properly. So that is the reason why this discharge time constant should be greater than 1 by Fc and less than 1 by W. So this is how charging or discharging is done. And as I said earlier, this will not work with when the modulation index is greater than 100. So we'll see what will happen when the modulation index is greater than 100. So for over modulation case, at zero crossings there will be phase reversal, something like this. So this is the AM wave when percentage modulation is greater than 100%. So at zero crossings there will be phase reversals. So now if we track this if we use envelope detector in this case, so the output will be something like this. This is how we get. So if we observe the output will be so like this. We get the output, but the actual output is like this one. So since it is being over modulated, the envelope will look something like this, which is not equal to the message signal. So that is the reason why we need to make sure that the percentage modulation is always less than 100%. Only then there will not be any envelope distortion. And so this is how envelope detector is used to detect the AM wave. Basically, we use a diode and capacitor. So during the positive half cycle, this will be charged. This capacitor will be charged, and when the diode is reverse biased, it will be discharged through this load resistor. So this charging time constant should be less than 1 by Fc, and the discharge time constant should be greater than 1 by Fc and less than 1 by W. So only then this charging will be done rapidly. This discharge should be slow, and it should not be too slow that it will not drive these minimum peaks. So after obtaining this by passing through the low pass filter, we can get the message signal. So if it is discharge rate is too small, so we cannot track the message signal properly, and if it is too large, these peaks will be missing. So we should lie between these two values, and this percentage modulation should also be less than 100%.